this video is going to introduce you to the normal model. We'll talk about z-scores, and then everything that we calculate here will be a integer z-score. So we'll use the empirical rule in order to find probabilities. So the z-score measures how many standard deviations a data value is above or below a mean. And you can find a z-score for really any distribution. It doesn't have to be a normal distribution, like that's the definition of a z-score. But what we are going to be talking about in this unit and for the rest of the course is normally distributed variables. So you have a continuous variable. We can use this notation here that says that it is a normal distribution with a given mean and standard deviation, and we can calculate this z-score here. If you have positive z-scores, then that means your x value must be bigger than the mean. If you have negative z-scores, then that means the x value must be smaller than the mean. And if x is equal to the mean, then you will have a z-score of 0. Now, the empirical rule tells us proportions or probabilities within a normal model based on standard deviations. So if you are only one standard deviation below or above the mean, then all of the data in your distribution between those two values would be 68%, or about 2/3. Between two standard deviations, you'd have 95%, and between three standard deviations, you would have 99.7%. If you have z-scores, note that one standard deviation below the mean would mean that z is equal to -1. One standard deviation above the mean means that z is equal to 1. And so on and so forth for all of your z-scores. Additionally, we can break up these percentages to find each individual percentage inside your normal distribution. So it's always going to be, with a normal distribution, it's always going to be unimodal, symmetric, and the mean and the median will be in the same relative place. So it is true that 50% of your data would be on each side of the mean because it is unimodal and symmetric. That is normally a median calculation, but because the distribution is unimodal and symmetric, the mean and the median are the same. So 50% of your data is in each half. That should make some sense here. Then where the curve changes from concave down to concave up, that is where your one standard deviation is going to be. We call those points of inflection, where the graph changes from being curved down to then that bell-shaped curve here. Well, if 68% is one standard deviation above and below the mean, then that means that 34% must be in each one of those pieces between that standard deviation calculation and the mean. So just taking 68 and dividing it into those two pieces. If I have -2 standard deviations and +2 standard deviations, this piece in between -2 and -1 ends up being 13.5. And between 1 and 2 is also 13.5. That gives us our 95% between those two. And then you can just label that 2.5% will be outside of each of those -2 and then +2 pieces. All right, let's look at an example of how we would apply this. So let's say that we have final exam scores for an introductory biology class at a large university. They're normally distributed with a mean of 75% and a standard deviation of 7.5. So we would say this is a normal distribution with a mean of 75 and a standard deviation of 7.5. And because they're grades, they're in percentages, but it's okay to just use them as whole numbers here. It's all kind of relative. So what does that mean? That means that I know that the exam scores look like this, with 75 in the middle. And, okay, 1 standard deviation below the mean means that I need to take 75 and subtract 7.5 or get 67.5. And 1 standard deviation above the mean means I need to add 7.5 on my number line or get 82.5. To get -2 standard deviations, I would then subtract another 7.5. And to get +2 standard deviations, I would add a 7.5. So then the question becomes on part A, what percent made a 90 or better? Well, here's my 90, and if you use the empirical rule up here, I know that this piece of a 90% or better, like this section of my data, is 2.5% of students. So that's my answer for A. If I want to know what percent of students made a 67.5 or lower, I could go here and be like, okay, this is the section of my distribution that I would like to look at. Well, I know that this is 2.5 and this is 13.5. And so together, this is about 16%. What percent of students made between a 67.5 and a 90%? Well, I can do this a couple different ways. I know that everything in here adds to 100%, and I already know these two pieces. This was 16%, and this was 2.5%. So I could just say 100 minus 16 minus 2.5, and that would get me what's left over here. I could also be like, okay, this piece is 68%. This piece is 13.5%. And both of these, it looks like, are going to give me 81.5%. Let me double check that, but I'm pretty sure. Yep, there we go. All right, so you can use the empirical rule here, especially when you have some like really close z-scores to 1, 2, or even 3. You can use the empirical rule in order to kind of shortcut or just approximate different probabilities here. Now, as far as a z-score calculation, if I wanted to do that, on this one, I would say z equals 90 minus 75 over 7.5. I get 15 over 7.5, which gives me 2, and that makes sense. Similarly, if I do 67.5 minus 75 over 7.5, I get negative 7.5 over 7.5. I get -1. That also makes sense. So that's how you can also use z-scores to find your location of your data points within a distribution.